Cool. So today we're going to continue our discussion on multimodal representation. Last week we saw unimodal representations, lots of language, vision representations. Today we're going to dive deeper into the content of multimodal representations. There's going to be two lectures this week, both on representations. Today I'm going to primarily cover fusion, and on Thursday we're going to primarily cover coordination and fission. So first up, as a recap for logistics, reading assignments have started. Week 3's reading assignment should have been posted. There's about 4 or 5 papers. Remember, the main timelines are that by Wednesday, you should be selecting the paper that you're most interested in, split it up among yourselves, your groups of 8 or 10. By Friday, you should post your summary of that paper. You should read that paper in detail, post your summary. And by next Monday, you should have discussed with your group mates, posted your extra discussion comments for those papers that you did not read, but your other group mates have read. Okay? Also, another quick recap is that pre-proposals are due soon. The instructions should be on Piazza. They're due tomorrow at 8 p.m. It's a very short document. Just 1 or 2 pages. It should state at the minimum what research problem you're trying to tackle. Remember the hypothesis, the research question, what data set you're going to use, what modalities that data set involves, and what prediction tasks are within that data set. So you should have chosen, or at least have a good idea of what data sets you're going to use. What are the multimodal challenges? Is it representation? Is it alignment? Is it reasoning, generation, and so on? What are the main multimodal challenges you're going to be working towards? And what evaluation metrics? Whether baseline models are available, publicly available, can you run them quickly? A quick sketch of ideas that you plan on proposing and working out throughout the semester. And also team members, split of workload, rough timelines, and milestones. And let us know if you have any extra computing needs that you want us to take into account of if you're working on large video data sets and the sort. All right, so one submission per team on Canvas. I think some people have wanted me to take to note out that after class today, people who don't have a team yet, or people who would like to spend the time to discuss with their team a bit more, can stay back after class. And also be available after class for students to discuss their research questions with me. Okay, so we're going to be doing that after class. So after you submit the pre-proposals, we're going to look through them, make sure that everything's on the right track. We're also going to be assigning you a primary TA. So this TA is the TA who you're going to be meeting with throughout the semester, roughly once a week or once every 2 weeks. And this TA is really going to give you a lot of feedback on your project. We're going to assign a primary TA, and for certain projects that may need some other expertise from the TAs, we're also going to assign a secondary TA. So this TA is going to most likely going to communicate with you the most throughout the project, but LP and I are also going to talk to all of you, talk to all the groups, and make sure all the projects are in the right shape. And those meetings will probably happen sometime next week and the week after. Any questions about logistics, about the reading assignments, lecture feedback, highlight forms, and the course project? Yeah, as I said, I'll be staying back after class so we can talk about any other specific questions you might have. And those people who don't have a group yet or who would like to discuss your groups a bit more can also stay back after class. We can meet somewhere outside. All right. So today we're going to dive into multimodal representations. We're going to look primarily at cross-modal interactions. The whole purpose of studying multimodal representations is to capture these interactions when your modalities are fused for some prediction task. We're going to look at representation fusion primarily today. And some examples of methods we're going to look at are additive, multiplicative fusion. We're going to go into gated fusion, things that dynamically change given your current input data. We're going to look at fusion on raw modalities instead of just pre-processed features. And we're also going to look at fusion that is made more heterogeneity aware to better deal with modalities that are very, very, very different from each other. And finally, we're also going to talk a little bit about how can you measure whether fusion has succeeded. And if you recall, the whole idea of measuring what your models are learning is really this key challenge in quantification. We're going to talk about that later in the semester, but just to give a glimpse of what quantification may look like, a glimpse of how you could measure whether your fusion has succeeded. So yes, multimodal representations. You recall we're going to use this schematic, right? If you have many different modalities coming in, like language, like vision or audio, like I really love this lecture, we're going to assume that these modalities can be broken down into individual elements. For example, if there's a sentence, it can be broken down into individual words. If there's a long video, it can be broken down into multiple frames. A long audio clip can be broken down into individual audio segments of me saying each word. We're going to use these shapes to represent individual elements, and we're going to use multiple shapes to represent the fact that there's multiple elements in your modality following some structure. And the whole goal of multimodal ML is to learn representations that summarize all these elements and all the structure within these elements into some representation that can be useful for predicting your label or maybe generating other modalities and so on. So the key first challenge, representation, we're going to assume that using all these elements, we're just going to focus on one of them. One element in your first modality, for example, one word, and one element in your second modality, for example, one object region. We're going to ignore the other elements first and ignore the structure between these elements to just focus on one local element at a time. So that's why we call this the most basic building block of multimodal learning, right? There's always going to be some elements at the local level. How do you combine them and form a representation for them? It can be seen as a local representation, or it can also be seen as a representation using holistic features. If I've taken all my language in my whole sentence and summarize them into one feature, or I take all my images with all the objects inside them and summarize into one feature, you again have one element from each modality without other elements. And we can also study representation fusion in that case. So representation, probably the most important challenge in multimodal learning, the most basic building block at the local level of two elements from two different modalities. And we mentioned three sub-challenges, right? Three sub-challenges in representation. The first one is fusion. Can I take in two elements from two different modalities and combine them into one representation that combines their information? We're going to talk about that today. Coordination is primarily about taking in two elements, learning two separate representations, but having them coordinated through some function, for example, a similarity function. And fission is about taking two elements and learning more representations that you start off, perhaps taking into account the fact that there's clustering in your data, or there's some shared versus unique information, which gives three representations from two modalities that you started with. So in fusion, the whole goal is to learn cross-modal interactions, right? This is one of the three key principles in multimodal learning. The fact that when you have two modalities and you combine them for some inference, there can be different types of information that arise that is useful for the inference of the task. So interactions happen only during inference. If you recall, if you don't have inference and you're just looking at two modalities, whether they share or don't share information, that was a challenge of connections. And we're actually going to get into that more during alignment challenge. So some examples of inference could be fusing them to form a representation. It could be predicting a task directly using supervised learning. It might be translating from one modality to the other. As long as you take two elements and you combine them, they're going to interact in the context of some task. So what are some examples of these interactions? I'm going to start very simple. Let's just say you have this image and you have a caption that roughly mostly describes the image. And if I ask you a task, is this indoors, right? You look at the image, you're probably going to say, yes, it's indoors. You look at a caption, a teacup in the room, probably yes, it's also indoors. So here's an example where the interaction is redundant, right? Both modalities giving you the same information in response to the task. And when you combine these two modalities, you're most likely going to get a yes with higher confidence. So that's an example of an interaction called enhancement. The fact that both modalities give you the same information for the task, and when combined together, they become more confident in that same prediction. Another example, this is a living room. You look at the image, you see a sofa, you see small tables, typically you see in living rooms, you answer yes. You look at a caption, you see a teacup, you see a clean and laptop, you might think it's a study room, right? So here's an example where two modalities give very different outcomes. It's called non-redundancy, two different outcomes. And when you combine both of them, one of the answers is correct, the fact that it is a living room as evidenced from the picture. The other prediction is not correct. So that's an example of dominance, where one of the modalities gives you the right outcome, which should dominate over the other. And finally, a last example, should I work here? Let's say you're looking for a place to work. You see the image, you might say, okay, it looks comfortable, there's a nice sofa, but the table's a bit too small. You see the caption by itself, you say, maybe, it seems the room is clean and there's tea. So again, it's an example of non-redundant, both modalities giving you different information. There's unique information in each modality that accounts for the different label. And when you finally make a decision, it can be a very complex combination of these, right? It depends on whether you're thirsty and you want tea. It depends on whether you can work with a small table or a big table. So the final answer is going to be an emergence based on contextualizing both of these modalities and can be different depending on different settings. So you recall in the first lecture, that was just a bit more detail from the first lecture, that there can be many different types of interactions. Whether the two modalities give the same outcome, that's redundancy, or different outcomes for the label, that's non-redundancy. In the case of redundant, the final outcome can be equivalent. So there's no interaction, you're still giving the same outcome with the same confidence, or it can enhance each other, right? Higher confidence in the same outcome. In the case of non-redundancy, it can be independence, where you have two different outcomes and both are preserved when I fuse them. One can dominate over the other, as we saw in the example earlier. One can contextualize or modulate the other. So you get one outcome, but with a different strength versus what it was before, or new information can emerge that is different from each of the individual outcomes. So the whole goal of representation and fusion is to learn models, typically machine learning models, that are able to capture these interactions. So there's several ways of categorizing these interactions. What we saw was typically by the response, how the response changes with respect to your input. You can also categorize them based on how many modalities are involved for these interactions. We're primarily going to talk about actually learning these interactions using machine learning models. For example, if I have an additive model that adds up these two modalities after I make predictions from each other, what interactions does that capture? If I have a multiplicative model or a polynomial model that's more complex interactions, what type of interactions can that learn? And if I use neural networks, if I take my modalities, use neural networks, what kind of interactions can that learn? There's many other ways of categorizing these interactions as well. One other way is connections, right? Whether the interactions are based on shared information between my modalities or based on unique information. We're going to talk about connections more on Thursday when we talk about coordinating or representations, and next week when we talk about alignment. But today, primarily about, there can be supervised data sets, but a caveat is that in order to exactly categorize what is, which data set involves dominance or emergence, you need the multimodal label. So when you have both modalities A and B, what the label is, but you actually also need the unimodal label. If I have only language, what a prediction will be. If I have only vision, what a prediction will be, right? So examples like this. Do I have, given this task, what inference on the language only is? Language only is, what the inference on the vision only is, and what the inference when I have both of them. So to actually study these interactions is not trivial because you typically don't have data sets that have both the multimodal label and also unimodal labels. These unimodal labels are typically hidden variables. But there are ways of perhaps inferring them using unimodal models or looking at how the multimodal prediction changes across your different data distributions. So even in supervised case, it may not be easy to precisely note down what interaction is required. In the unsupervised case, it can get even more difficult. But of course, nowadays you see lots of examples where you first do unsupervised pre-training or mouse pre-training without the label, and then you fine-tune it for the label. So that could also give an opportunity. So dominance doesn't mean the other modality is useless, because in many cases, the dominance switches between modalities, right? In like healthcare or like self-driving cars, all these cases where you have physical sensors, where there's a cost to collect the sensor, you typically think if one sensor is enough, I'm going to use it. If it's not enough, I'm going to collect one more. You're not going to collect more modalities for the fun of it. So the key there is to figure out when is this modality enough and I don't have to use the other, or when is the other modality enough and I don't have to use the first. One quick note about redundancy as well, right? When two modalities are redundant, it doesn't mean that they're useless. It doesn't mean that you can just do unimodal. As you see, there's cases where they can enhance each other, so you become more confident in your prediction. But also there's this whole field of study that if you have two modalities that give the same information, they become more robust. If I drop the first one, you can use the second one. If I drop the second one, you can use the first one. So even in traditional machine learning, when we look at mixture of experts, when we look at ensemble methods, they're designed to give similar information, but more robust in case each one of them are imperfect. The student at back, do you want to find a seat to sit down? Okay, so representation fusion. We're really going to dive into the details of how can I actually learn these models that take in two elements and learn one combined representation. And when we think of representation fusion, we want to think of a spectrum. The first spectrum involves what we call basic fusion. So in this case, you have two elements of different modalities. They might be very different in their raw data, but I've already extracted features from them such that you get representations that are more homogeneous in nature. Right? If I pass language through LSTM, so transformers, you get language embeddings. You pass images to pre-trained vision models, you get vision embeddings. They're more homogeneous because they refer to almost typically the same semantic concepts. If you have these encoders and you bring representations into more homogeneous space, then fusion becomes easier. The fusion model can typically be smaller. The other spectrum is more raw modality fusion, where you don't want to use pre-trained unimodal encoders for some reason, for example, because you don't know what unimodal encoders to choose. You don't want the errors to propagate in the case of bad unimodal encoders, or even settings where you don't have good pre-trained unimodal encoders for time series or physical sensors. In which case, you might start with the raw data, which can be very different in nature. We call raw data is more heterogeneous than abstracted representations. And in which case, you need to spend more time designing your fusion. Right? The fusion has to do more heavy lifting in order to fuse these very heterogeneous modalities. There's going to be pros and cons of both. We're going to start with raw modality, basic fusion, where you've already extracted features and the fusion is simpler. And then towards the end of the lecture, we're going to talk more about fusion with raw modalities, where the fusion might be more complex. So fusion unimodal encoders, right? You're going to first assume that there are some good encoders you've extracted for each modality. You can learn features, and the goal is to fuse them for some task. For example, language, image through image encoders that are pre-trained, language through other language representations like BERT that are pre-trained. So in fact, a historical view of fusion is that, back before multimodal deep learning and all these recent innovations of machine learning, there are only two types of fusion, early fusion and late fusion. And typically what everyone did was to first take your modalities, extract the best features from each modality, and early fusion will concatenate these features and train a predictor to your label. And late fusion would train individual predictors from each modality to the label and take an ensemble, right? See which one is most confident, or if you have more than two modalities, what is the majority vote? So that was a historical view. But of course, now we know that there's many, many more different types of fusion that can outperform early fusion and late fusion. But still, these are very strong baselines, right? Whenever you start with a multimodal problem, start with unimodal predictors, unimodal models, see how. But since then, we moved beyond early and late fusion. We've looked at many different fusion methods. Many different fusion methods have been invented to learn different types of cross-modal interactions. So we're going to start simple. Let's just start with a univariate case where each feature from each modality is one dimension, xa, xb, and the target that you're trying to predict, z, is also one dimension. So the z can be a next layer of a neural network, or it can directly be the label you're trying to predict, say for regression. So in the most simple univariate case, and we're also going to look at simple linear models, one general way of designing fusion is to have your output z be equal to W0. So that's a constant, a bias term that is learned. There's going to be some error that you can't possibly model in this real world system. And it's going to be a linear function, W1 on XA, plus a linear function, W2 on XB. These are called additive terms. And there's a function that takes a multiplication of XA and XB with some weight designed for that multiplicative term. So very simple linear model, right? It's a slight extension of linear regression because in linear regression, you don't typically see these multiplicative terms. But in a second, we'll see why these multiplicative model, and you can use it to test hypothesis. For example, I'm going to give a real world data set. Let's say this data set consists of people speaking in front of the camera and they're reviewing a book. I'm going to collect two features. The first feature, XA, is the percentage of the time the person is smiling and giving that review. So from 0 to 100% of the time smiling. The second feature that I'm going to collect, XB, is a binary feature, whether a person is a book critic, 1, or a person is not a book critic, 0. So critic means people who review books professionally. And Y is going to be a target of how good the book actually is. And let's say I get this target score based on an average of people who read this book, say on Google Books or something. And my goal is to learn a predictive model that predicts Y, my audience score, given these two features, the percentage of the time the person was smiling as they reviewed the book, and whether the person was a professional critic. And I might have two hypotheses. My first hypothesis is, does smiling, so my first feature, XA, does smiling reveal what the audience score was? That's my first hypothesis. And my second hypothesis is an interesting one. Does the effect of smiling depend on professional status? Right? So you're not actually taking a relationship between the features and the label, but rather relationships between two features, XA and XB. Right? XA, smiling, and XB, whether the person was a critic or not. And start training these linear regression models on my data. I can learn all these terms. W0 is the average score when both XA and XB are 0, when the person is not smiling, and when the person is not a critic. That's the bias term. I can learn W1, the effect of XA, how much when a person increases a smile, how much that would increase the audience score. W2, that's the effect of XB. When I go from non-critic to critic, how much that influences the audience score. And finally, the effect from XA and XB together, multiply together, and find the residual. So what might this look like? So let's just say I'll just train a model using only my XA feature. All of you have seen this, right? I can plot my smile XA on the x-axis, and I can plot the score Y on the y-axis. And this slope is given by W1. So that's the value telling me as I increase the percentage of time the person is smiling in a video, how much I increase the audience score as perceived by the audience for the book. And that answers, does smiling reveal what the audience score is? You can train this linear regression model, and given any value of someone smiling, you can predict how much the audience score would be, for example, for a new book. And you can look at what these estimates are, right? W1 might be 4.6. That means even when a person is not smiling, this book on average has a score of 4.6, and W1 is 1.2. So slightly larger than the identity function. So this basically tells me that the effect is significant. There is a strong effect of the person smiling on how good the book is. So I can also train an additive model. And what that will look like in a graph will be something like this. So again, I have two lines. I have two lines because my XB function is binary, is 0 or 1. Right? So one of these lines will be the case where XB is 0. That's the red line. And one of these lines will be a case where XB is 1. That's the blue line. And there's something very interesting about these two lines, right? They're parallel. What that basically means is that when XB is 0, I have a linear relationship between smiling and the label. And that linear relationship is given by W1. And when XB changes to 1, the whole graph shifts down, right? The same curve, there's the same linear relationship between smiling and the label given by W1, but the amount that it is shifted down by is given by W2. So in general, there is still a positive relationship. When I smile more, when the person in the video smiles more, the audience score is higher with a coefficient of 1.19. But when I go from a video where the person is not a critic, where XB is 0, to a video where the person is a critic, the overall score drops by negative 1.7. Typically reflecting the assumption or the intuition that critics are more harsh on reviewing books. So that's a simple example of how you can use two variables in predicting a label. This model is going to be more powerful, more expressive than the previous model we saw, which only used the presence of smiles to predict the score for the book. But you can see there's a limitation here. When you use a linear model like this, you're going to end up with two lines that are parallel. You can't model more expressive functions than that. So what happens when we use a multiplicative model that has both additive terms, linear terms, XA and XB, and also a multiplicative term that takes into account XA and XB together? You can plot this and see something like this, right? There's a nonlinear relationship between XA and XB, in which case the two curves may not be parallel anymore. And what this curve is saying is that when this person is a critic, so when the blue line is above the red line, when the person is a critic, when they smile more, they give higher scores than if they were not a critic. But when a person is a critic and when they smile less, they give lower scores as compared to not being a critic. So in some sense, critics are more polarizing. On one end of the spectrum, when they smile more, they really give higher scores than the average person. And when they smile really very little, they give much harsher scores than a normal person. So that's an example of a multiplicative effect, right? Essentially, the effect of smiling on professional status is conditioned on what the professional status is. And this multiplicative effect therefore gives you even more expressive models than if you just had individual additive effects added up, which then gives more expressive models than only using one of the features and not both of the features. So over here, W3 shows a multiplicative interaction. And in this case, the multiplicative interaction is positive, essentially saying that when I go from not critic to critic, and when I smile more, that gives a more positive effect on predicting what the audience score is. So yes, a simple example and illustration of when multiplicative interactions can be more expressive than just additive interactions. Any questions so far? Any questions about this simple illustration of additive and multiplicative? Mentioned that there can be cases where this exact multiplicative term xa times xb may not be the most useful. I think example was that if xa and xb are always constrained such that they multiply to 1. So as 1 increases, 1 decreases by 1 over the other variable, then this is always a constant, and this would always be not very useful. Of course, that could be possible. A contrived case, but it could be possible. And so there's other multiplicative terms you can add. And we'll get into that in a little bit. Higher order polynomials, for example. If you really believe that xa divided by xb is a useful feature, you could probably add that as well and have another coefficient learn it. And of course, you can also add things like xa to the second power, xb to the third power, and so on. These are going to be more expressive. Of course, the trade-off comes in the sense that you're going to need more variables. Back to multivariate case. That was just one dimension. Let's say you're working with actual features in machine learning, and xa and xb are multiple dimensions, and likewise z, the next layer of your neural network or your prediction task, is also multiple dimensions. So you can again define additive fusion. Additive fusion requires that xa and xb are at least the same dimension, but you can learn weights w1 and w2. They are also multidimensional. So in this case, xa and xb are 4 dimensions. w1, w2 can also be 4 dimensions, in which case you take element-wise product for each dimension of w1 with each dimension of xa and xb. And again, the addition will be element-wise. And likewise, you can think of it with encoders. If I have maybe some prediction function, fa on the first modality and fb on the second modality, additive fusion is simple, right? Just add the predictions in the end. This can also be seen as late fusion or an ensemble where you predict each modality individually and just add up at the end. So that's additive fusion. Of course, we saw that multiplicative fusion can make things more expressive. So you can also do element-wise multiplication of xa and xb, element-wise, get the same dimensional vector, and learn a weight w on top of that to process for the next layer. But of course, that doesn't take into account all possible multiplicative interactions, right? A more general form is to take element-wise, every element in xa with every other element in xb. So what you end up is with this matrix that contains all pairwise relationships between xa and xb across multiple dimensions. This is typically called bilinear fusion and can be achieved by an outer product between xa and xb. But if you do that, all you get is multiplicative values. You don't get any additive values. You don't get each modality individually. So one trick in order to get both multiplicative and additive is to append a 1. Append a 1 behind xa, append a 1 behind xb, do the same bilinear outer product. And what you're going to get is a Z matrix of dimension 1 more in the row space in the column. And this 1 actually allows you to take the individual XA feature, individual XB feature, as well as a 1 that allows you to learn the constant. All right, so XA append 1, outer product with XB append 1. So you take unimodal features in which you would learn weights. Those would be additive contributions. And you can also learn bimodal features, and after which you learn a weight, that would be a multiplicative interaction. And finally, if you do it for 3 modalities, you get this very cool graphic here called tensor fusion, where you have a 3-dimensional tensor representing all 3-way interactions. You get a 2-way interaction as spaces on the cube. You get a unimodal additive interactions as sides on the cube, and you also have a 1 hidden all the way in the background, in the back corner of the cube. So a general way of learning different dimensions of interactions, different orders of interactions from 0 order, that's a constant, first order for additive, second order between 2 modalities, and third order between 3 modalities. And typically this, you can then put it into the next layer of your model, your neural network. But issue then is that the next layer is going to be very, very large dimension, right? If this is 4, 4, 4, this already becomes 64. And the next layer is like 10 dimensions. You need a 64 times 10 dimensional weight in order to go to the next layer. But there are some cool ways of learning these interactions while not being so computationally expensive. So here's an example called low-rank fusion. This basically borrows the idea from the fact that any matrix can be decomposed into a sum of individual outer products of vectors, right? And a number of sums of these outer products is given by the rank of the matrix. Likewise, you can do it for tensors. So I have two modalities, two vectors, and I take this outer product, that becomes a matrix. And if I have a next layer of my neural network called H, this weight matrix is going to be expensive. It's going to be whatever dimension this matrix is, multiplied by number of dimensions in my H. So that's going to be expensive. I can actually decompose this into a product of individual outer products of these matrices. Right? In a matrix case, I can decompose my matrix into just this outer product with this, sum over multiple times. Because in this case, you have a H dimension at the back, you can get an outer product between this matrix and that other matrix. And the number of times I have to do this summation in order to fully reconstruct my tensor is given by the rank of the tensor. But in practice, most of these tensors are not very high rank. That's why we call this low rank decomposition, or in other words, low rank approximation. Yes?
The weight matrices have low
rank. Right. The assumption is that these weight matrices are going to have low rank. So if you have to use as many as the actual dimensions, so it's full rank, then you don't get any savings in cost. But if your weight matrix is actually just rank 2 or 3, then you can just use 2 or 3 of these summations of outer products and still learn something reasonably close to the weight matrix. Maybe hyperparameter, yeah. And these folks show that the weight matrix that you actually end up learning through gradient descent can be of pretty low rank. Good question. So you can decompose that weight matrix with respect to hyperparameter, however higher rank you estimate it to be an outer product of these summation of these outer products. You can likewise, instead of actually creating this matrix, just keep the two vectors by themselves, because this matrix was the outer product representation of these two individual vectors. I can just keep the individual vectors themselves. And you can actually prove that you can rearrange the computation and get something equivalent, right? Just take my first vector, multiply by each of these low rank factors for that modality, and I multiply with my second feature, with my second modality, multiply with the weight matrices in the second modality. And it's actually equivalent to actually constructing the high rank tensor and actually doing the multiplication. So this is called tensor fusion with low rank. Essentially, 3 key ideas. I'm going to take a decomposition of my weight matrix into these sum of low rank factors. I'm going to not actually create this input matrix and I keep them as the input features themselves. And I can rearrange the computation to get something really efficient. I can leave you to look at the mathematical details in this paper, but essentially a very efficient way of learning the actual output, even though the intermediate steps, if you compute them exactly, can have very high dimension. Form of fusion. So just like say additive or element-wise multiplicative without creating a tensor. And then tensor fusion came out, and tensor fusion showed that you could do better than these things without tensor fusion with more computational costs. And this low rank fusion approached the performance of tensor fusion, right, with much lower cost, and they were still better than the individual additive and multiplicative fusion. The key idea here is that you are still considering element-wise multiplicative interactions, right? It's just that the weight matrix that you use to process them afterwards and do the next layer of the model may not be high rank. And if you actually train a model from scratch, if you do the full rank version and you train it from scratch and you do SVD afterwards, you're going to see that the singular values drop by very quickly. So in fact, even if you train it from scratch, you're not going to get something very high rank. I mean, neural networks in general are pretty over-parameterized. If you all follow the literature, and a lot of the weights that actually end up being learned are not going to be fully high rank. Okay. Any other questions about tensor fusion and low rank tensor fusion? Yes. Right. So in this case, the very first paper was a hyperparameter. So I'm just going to say, let's say my W is 5 by 5 by 3. I'm just going to say the rank is at most 2 or something, or maybe 3, whatever hyperparameter is. So, and then based on the hyperparameter, you're going to adjust how many of these summations of outer products you're going to have. Right. So the higher the hyperparameter, the more computationally expensive, but it might go closer to what the real matrix is. But if you actually have a weight matrix to compute its rank, you can do something at SVD and get the singular values and see how much it drops to something close to 0. Right. So that was tensor fusion. And of course, you can go even more, right? If you really believe that first order interaction is not enough, second order with additive and multiplicative are still not enough, and you really want to go to like tensor and even more, like for example, like different orders of polynomials, if you really think these are useful, then you can do that as well. I think tensor fusion and the whole research of tensors has studied learning these interactions in detail. I'll get into that in a little bit. We're going to talk about, firstly, from a methodology point of view, we're going to talk about fusion with just like added concatenation and putting all these models. We're going to analyze what interactions these may learn and how it may be different from these. But to answer your other question about what types of inductive bias would lead you to choose some of these fusion types, I mean, you got to know your data, right? Some people, in some scenarios, believe that there are higher order interactions in their data, in which case it'd be good to explicitly model them using a multiplication of higher orders. Sometimes you believe that your data is going to be more redundant, so all these interactions may not help. So it really goes back to what I was giving at the beginning of cross-modal interactions, right? You're going to see your data, you're going to look at some data points, you're going to think, okay, in this case, both modalities give the same outcome. I smile and I say something positive, same outcome. In these cases, I'm angry, but I say something positive. Oh, there's an interaction. I'm being sarcastic. Right? So you're going to look at your data, you're going to realize which of these interactions may be necessary. And you also have some intuition with what multiplicative gives you that additive may not give you, right? As we showed in the example previously. But I mean, multimodal is very, very heuristic, empirical based. There is no one theorem that says, here's the data, here's the list of interactions, here is the model that learns it. It has to be second order in XA, but first order in XB. There isn't really such a theorem. People are working towards it, but as of right now, there isn't a precise theorem that tells you what model to choose. So to recap, right, you got to understand your data. You got to understand what interactions are in your data. And then you got to look at some of these models. You got to understand these models and what interactions they might capture. That can be done from a more theoretical perspective. It can be done from more empirical perspective. We're going to give more examples later. And at some point, you got to kind of match what interactions you expect in your data with what interactions you expect your models to be able to give you. So you can do statistical analysis in your data set to see its distribution. All that could be extended to interactions. It hasn't been studied that much in that much detail, but I think there are possible research directions for this. One simple example, and I'll talk about this more in quantification, is like, I don't know if people are familiar with like gradient-based analysis for unimodal. If I have an image classifier to some label, I can look at the output gradient with respect to individual pixels, and it should highlight the region of interest in that image and actually let the model to make that prediction, right? So in unimodal, you can do that. In multimodal, you can also do something like that, where you can take an image and text, a fusion model, predict some label, and you can take a gradient of the label with respect to image, get whatever image was most activated, and get a second order gradient with respect to the text to see what text was most activated for those image regions that were most activated. So that kind of tells you how much interaction there could be. And there's other papers as well. I'll try to link them on Piazza, but in quantification, we'll talk about that in more detail. Yeah. It's a nice comparison. I wouldn't say it's hand designing as much as in every machine learning design, even in deep learning, you're going to have inductive biases, right? Self-attention was designed for this type of bias. Graph neural networks have this type of inductive bias. This is in some sense the inductive bias for representation fusion in multimodal. But of course, all these are still compatible with deep learning, right? You're going to eventually learn these end-to-end, where your data comes in, you have features, you define some architectural type. It can be this, it can be transformer, going to get the output. So a mix of hand designing, but very much also train end-to-end. Sorry, folks, anyone have a Mac charger? All right, good questions. And all these questions are very good questions for research project, right? It's good in the sense that it's not just another architecture that you're building for a task to get higher performance, but you're really asking very fundamental questions about multimodal, right? I think the question was, how do you, for example, in data sets, figure out what interaction may exist? There's been some preliminary work, but really diving deep into that, coming up with core empirical or theoretical methods to do that would be perfect. Different ways of doing model selection as these two students mentioned as well. Okay, so in general, it can also be extended. Any high order interactions beyond additive, multiplicative, second and third order, you can learn it, and the general recipe is the same, right? If I have two features, Z1, Z2, concatenate them, append the 1, so that when you actually multiply it with the self, you're getting both the highest order interaction as well as the intermediate low order interactions whenever the 1 is getting multiplied. All right. In general, you can define a hyperparameter P. That gives a maximum order you might learn. The issue is that the weight matrix to the next layer is going to have dimension P plus 1, right? Or order P plus 1, which might be expensive. But in general, you can do low rank approximations to get a final output. So these folks regeneralize a lot of what we said into something that's more flexible. Just have to define the hyperparameter P, and the model will automatically learn interactions from order 1 all the way to P. Okay? Yep, so that's the end of discussing these high order interactions designed by hand. There are other ways called gated fusion. Gated fusion is fundamentally different because everything we've seen so far, the weight matrix is always fixed, right? The weight matrix W1, XA, W2, XB, the W1, W2 are always fixed for all data points. So the next set of methods, we call it more gated or dynamic fusion, where these weights may depend on the input data itself. All right, so XA, my feature, you might learn a gate. For XB, a feature, you might learn a gate and get the weight matrices W1 and W2. But now these weight matrices are functions of XA and XB. Right? So instead of writing W1, which is a static weight, you can write it as GA as a function of XA and XB. So GA and GB can be seen as attention functions. Given different inputs, it's going to automatically decide what to focus on in the inputs. And again, the gating output can be one-dimensional, multiply element-wise to every dimension of a modality. It can also be the same dimension as the modality, and you do element-wise multiplication. And two interpretations, right? It can be thought of as a model that prevents useless information from going in, or it can be seen as a model designed to filter out the most important information, attention. And you can do it using soft attention, where the gates are learned through a softmax. They're going to be 0, 1 values, real value. Or it can be hard attention, where you want these gates to be just 1 or 0, right? Both have their benefits. Soft attention is much easier to optimize. It can be done end-to-end. Hard attention, it can be harder to optimize when these values are binary, but it gives much sharper attention, right? You're just saying this go in, this doesn't go in to the next representation. And these inputs can be based on the modality that you started with. So that can be thought of as self-attention. Given my current modality, I'm using that to learn a weight for that modality itself, reminiscent of self-attention. It can be the other modality. So essentially where the other modality tells you how much it can be, the weight should be, or using both modalities. So typically when you see cross-modal attention in transformers, it's going to use a function of both modalities to determine that weight. But we're going to go more into transformers. Okay, so that's gated attention. So modality shifting fusion borrows some ideas from gated attention or gated fusion, but it's going to make an assumption that one modality is primary. One modality is the most powerful, and the other modalities are only meant to help that modality. Nowadays, one good example of that is where the primary modality is language or some pre-trained language model. You know that is super powerful model. XA and XB and XC, your other modalities are maybe audio, visual, other modalities. You want them to shift the language representation by a bit, but you don't want it to change that much because, you know, the language representations are going to be really good by themselves already. So in that case, XB and XC will go through a gate, again, some of these gating functions to learn a feature that is used to shift, right? It's only going to be a small additive component on this primary modality. So usually, for example, primary modality could be language and secondary modalities could be audio and visual. One example is, you know, the word expectations is pretty neutral by itself. You don't want to change the word embedding too much because it has lots of structure with respect to other words, but you're just going to use the audio visual information to shift it a little bit towards negative if the person saying it is disappointed, or shift it to more positive if the person saying it is more excited. So that's modality shifting fusion. And finally, mixture of fusions, right? If you don't really know what to choose, you can use multiple fusion strategies, each with a different gate. You can choose between unimodal, additive, bilinear, and so on, and get your output. So again, the gating can be solved the harder tension. And the more you do this, the less inductive bias you have, right? At this point, basically admitting that you don't know which of these fusion strategies to prioritize. I'm just going to do a purely data-driven way to let my model figure out from data which of these fusion strategies are the best. And of course, when I say purely data-driven, some of you probably thought of the simplest case, right? Nonlinear early fusion, where you just take your modalities, concatenate them as early as possible, and define a big model, a neural network transformer, and let the model figure out what fusion strategy to choose based directly on the data. So that recovers early fusion. Yes. So you can define many different fusion strategies. So maybe a unimodal model gives you some outcome, additive model gives you some outcome, a gated fusion gives you some outcome, and you can get it to the label level or even representation level. And you can use a gate to determine what weight to assign to each of these models. Yes. In the extreme case, nonlinear, early fusion, and you let your neural network try to learn everything. And of course, the question that becomes, right? We've talked so much about the inductive biases of fusion, additive, multiplicative, polynomials. If I just define a neural network, is it going to learn the same thing? So here's a very interesting paper. I'd like to go into a bit of detail. Essentially, what this paper studies is that let's just say I have done early fusion. I have taken XC and XD, concatenated as early as I could, define a big neural network to break a label. So what interactions does this neural network actually learn? So I'm going to define a projection because I'm going to take this neural network F. I'm going to try to find the closest function that is just additive in nature, FA and FB, right? So essentially taking all these complex models, which they're not additive, right? These are very complex nonlinear models. I'm going to project them into the closest models in my space of additive models. And as a way of actually doing that exactly, if I have my original function f, I take an expectation over xb. So marginalize over xd, and that gives me a function that depends only on fa, right? Modality A. I'm going to take that same nonlinear model. I'm going to take an expectation over xa. That will marginalize xa out. That gives me a function just depending on xd. And this is basically my approximation for my original model. So if this approximation is equal to my original model, that means my original model only learned an additive function. It's nothing more than an additive function. If this approximation is very far from my original model, that means my original model learned much more than this additive function. Make sense? So what I can then do is I can train all these nonlinear models, neural networks, SVMs, MERT, LX-MERT, pre-trained models. I can train them on my data sets, see what performance I get. I can define a linear model, and I can do the best model plus EMAP, essentially taking all these nonlinear models and just projecting them into an additive function, f of A plus f of B, right? And look at what performance drop there was when I projected from nonlinear complex models into these simple additive models. And I found that in some cases, the drop is not that much, right? You can get 91.3 using the most nonlinear, kernel SVM, but it just drops 91.1 when I project into a mix, into an addition of FA plus F of B additive functions. I can get like 53.4, or in this case, I get 64.1 using this nonlinear neural network on top of some pre-trained model. If I project them into addition of f of A plus f of B, I still get 64.1. So that means sometimes you can train very complex models. You think they're learning nonlinear interactions, but at the end of the day, they might be only recovering very simple additive functions. So here's an example of quantification, right? Where you want to train a model, but you always want to do a sanity check. Is my model actually learning something nonlinear, higher order interactions, or is it just learning something that? And if that happens, then the question becomes, how can we try to make our models learn more than additive? And there are ways of doing that. Here's a very neat paper. If I have many modalities and has different types of interactions, unimodal, bimodal, and trimodal that I want to learn, I'm not going to learn everything at the same time. I'm going to prioritize the learning of simpler interactions first before I learn the more complex interactions. So for example, I'm going to first take my features, just do an additive fusion. Additive fusion with weights on each modality only gives me unimodal contributions, right? So I'm going to take whatever unimodal that was, and I'm going to try to predict the label. Try to minimize the loss between what my actual label was and what the output from the unimodal model was. I'm going to minimize that. Try to get the most out of my unimodal additive functions. And it's not going to be perfect, right? There's going to be some residual that I'm not going to be able to learn just from these unimodal additive functions. So I'm going to then train bimodal models using combinations of A and C, B and C, A and B to fit that residual, to fit the remaining error. And again, that might not be perfect. There's still some parts that need trimodal. So I only use the residual to fit the trimodal functions of XA, B, and C together. And at any point, I can stop, right? If I think my loss is small enough, it's 0.2 is small enough, and I don't want to use more parameters to learn the rest, I can stop. If I think a loss is too high, like 3 or something, I want to minimize the next loss, I can go further. I can go further on. So here's a way of prioritizing simpler interactions using this recursive process. And you're guaranteed to minimize the loss at every step, right? Because you're only minimizing the residual using the new features. Okay. Any questions so far? Any questions about the projection into additive models and also this residual method? Yes. So let's say F is my very complex function, right? F is a neural network that you might have trained on A and B to bring the label. So the nearest additive function is you take F, and I'm going to take an expectation over XB. So put in all the XBs that I can, see what the output is, and take an expectation over all XB that you have in your data. So you take an expectation over XB, you essentially marginalize it out, right? So what remains is a function that's only dependent on XA. Well, think about this. I have a bunch of images and captions, right? I have a bunch of images and captions, and I've trained a model that takes in images and captions and predicts some outcome. So that function that I trained, I'm going to use the first image. I'm going to give it all captions. I'm going to put in all captions with the first image and take an average. And for the second image, I'm also going to take in all possible captions, put it in, take the average, and so on. So for each of the images, for each of the XAs, I take an expectation over the second modality. Right? And so basically, you've seen all of the second modalities, right? There's nothing else to depend on in XB. So now the function depends only on XA. And vice versa. So this actually shows, you can actually prove that any function f, you can take expectation over XA, you can take expectation over XB, you get the two additive components, and it's going to be some residual mu left over. The residual mu left over basically tells you how much my original function f was more than just this additive function. Right, but essentially they found out that this mu, how much it was more than just additive, was very small. Yeah. That is an interesting hypothesis. It'd be cool to see that in practice. I think you're basically saying that under a range of values for y, say like between 0, 1, a uniform or something, additive and multiplicative are going to be very close together. Right. I think there are certain distributions that you could find where additive and multiplicative are very similar. Whether it's the case for these data sets would be a very interesting research question. And that is one valid hypothesis. I think what these folks claim in their paper is probably that these data sets just may not require more than additive interactions. How to test that hypothesis, I'm not sure. It requires you to kind of know the ideal data generating function for these data sets, but also, again, a good question. But I think the intuition makes sense. Like some of these are like Instagram posts where the image and caption, and you know, if you use Instagram, you always write captions that are descriptive of the image, right? So in many cases, they provide similar information. They go back to redundancy. They go back to the redundant interactions that I talked about at the beginning of class. And I think they also did some more experiments. If you have something like VQA, where the goal is to explicitly toggle between modalities, right? Like for the same image, I can ask this question, you get this answer. For the same image, I ask a different question, you get a different answer. Then these additive projections are going to be quite far off from the original function. But yeah, so I like this paper. I think all these are good research questions. you could look at for the first half. Fusion with more features, right? In all these cases, we saw the features. We would assume that the features are pretty good. They're more homogeneous. They share the same semantic meanings. So the fusion is still at a stage relatively simple. You're just doing additive, multiplicative functions on top of these features. The other big paradigm is to do fusion with more raw modalities, because you're worried you can't define the features well, or you just don't have features that are pre-trained for certain modalities. So I'm still stuck with modalities A and B that are more heterogeneous in nature. And in which case you might have to do more in the fusion. But a good thing is that nowadays, with all these inventions in transformers, even though modalities are very different in their raw data, they can be processed actually quite similarly. Right? We've seen that transformers on raw text, you can use self-attention to learn language features. And nowadays, you also have these like image transformers with like mass pre-training that can take raw image patches and learn good representations for them. Right? So we're going to talk more about these image transformers next week. But essentially, what you can do is that you can define language, for example, language using raw data tokens, transformer models. For image, you can also get them into individual patches, define some of these mass transformer models, and you can still get pretty good representations that can be stitched together for fusion. So one particular innovation that is interesting to me is that when you have these raw data, when do you fuse? Right? You can define these transformers with multiple layers for each of them, but when is the right stage to actually fuse them together? So here's a cool word called dynamic fusion, early fusion, because you're still combining them at a very early level. But what you can do is that you can figure out whether I should do more unimodal processing at this stage, or should I fuse at this stage? And likewise, at the second stage, should I do more unimodal processing, or should I fuse? And so on. Right. So essentially deciding at which stage have I done enough unimodal processing to fuse. And this is super suitable for modalities that are more heterogeneous in nature. Right? You don't know whether you've done enough unimodal processing to bring them more homogeneous to fuse. So you can let the model automatically decide it for you. So essentially what that means is that a fusion is fully learned from data. And there's several extensions of this based on architecture search, where again, you can define basic unimodal building blocks. Right? I might do a ReLU, convolution, self-attention. These are unimodal functions. You can define some basic fusion building blocks like concatenation, attention, additive, multiplicative, and so on. And I can automatically search for the best sequence of actions to take in order to decide when to do unimodal processing or when to do fusion. Right? So it's a purely data-driven way. And that also, folks found this works pretty well for fusion with more heterogeneous modalities. In this case, it was electronic health records, where the images are like X-ray images. You don't really have very good pre-trained models for them, and the text is medical text. And you can design this way to automatically figure out when I should fuse these very heterogeneous modalities. Another general paradigm for dealing with heterogeneity is figuring out which modalities are more similar and which modalities are more different for fusion. So some modalities can be very similar with each other, and you can essentially do this using a transfer learning perspective. If I train a model on my modality, how well does it transfer to other modalities? Right? There are other modalities I may transfer very well to, like in this case, the blue and yellow, and other modalities I transfer terribly to. Right? And likewise, I can do this with my fusion. Right? These two modalities, you can train a fusion model using additive or multiplicative, and using that exact same model, how well can I use that to fuse another pair of modalities? Right? Certain modality pairs can be fused in the same way. Certain modality pairs may be fused very differently. So essentially, this gives you a way to deal with heterogeneity, because essentially telling you is allowing you to estimate which modalities are more similar to each other, in which case I could fuse them more easily, and which modalities are very different from each other, in which case I might have to fuse them or represent them very differently. So that enables you to get these matrices that essentially tell you for every modality how similar or how different they are to other modalities, and likewise for every pair of modalities how similar or different they are to other pairs of modalities. Right? Using that, you can determine which of them are similar to have the same fusion, or which are different to have different fusion. So in this case, green and purple are very different. They don't transfer well. There's a very large distance between them and other modalities. And likewise, the fusion of this blue and green is very different from other modalities. Yes?
The metrics used to say that single?
Right, so the transfer approach, right? If I train a model on one modality to predict the label, to what extent can I either zero shot or few shot fine tune it for these other modalities? Some transfer really well, some transfer not so well. And that also gives you a good way of dealing with modalities and fusion that is more heterogeneous. Yes? Sorry?
Can you explain these matrices again?
Right, so these matrices essentially tally for every modality and to all the other modalities, their distances. Right? Distance of 0 basically means it's always distance of 0 to itself, but distance of 1 basically means in this case that blue can transfer very well to red. So I train a model on blue and I fine tune it to the label and I zero shot or few shot transfer it to red, it's going to perform very well. But in this case, green, right? Green or purple, you're going to see that the numbers are all pretty large. Essentially, that means that if I train a model on purple and I try to transfer it to all these other modalities, the performance is not very good. Right? Essentially meaning that purple is more different in its raw modalities as compared to the others. Yeah. Oh yeah, okay. So one shot, few shot basically means how many label data points are used, typically. So if I train a model on purple, right? I have a trained model from purple to predict the label, and I just test it on red data. That's zero shot. Yeah, no fine tuning. Right? If I like one shot, meaning I give like one label of red data and its label. So zero shot definitely wouldn't work because it's a complete different input space. Few shot is something that could work, but you also can't do many shot, right? Because if you train it to the limit, then it's just going to do well regardless of what it was initialized by. Right? If I initialize it randomly or initialize it from a model trained on purple, and I have like unlimited data from red, it's going to eventually converge to something similar. So you need something like, you can't give that much data in order to test how well it transfers to another modality. Yeah, great question. So what we can do with this is that you can then decide whether to use the same model for modalities that are more similar, or you might use a separate model for modalities that are more different in a unimodal case. So that's given by how different the modalities are to each other. And when you're fusing these, you can also use insights where these modalities can be fused very similarly because they transfer well. And these pairs of modalities might require separate fusion. And this pair might again require separate fusion. So this is actually a result that enables you to kind of scale your fusion to many modalities, some of which were more heterogeneous in nature, some of which were more similar, homogeneous in nature, but you didn't really know what. Yeah. Question?
Yeah. So what differentiates few shot from like fine tuning then? Is it just the number of label data points we get?
I mean, people usually say few shot fine tuning, right? 5-shot fine tuning, 10-shot fine tuning, just a term to specify how many examples. Tuning for every modality, you train a model on it. How well does that model transfer to some other modality?
Okay.
Right. So I mean, these numbers are not actually how well it transfers. They're kind of normalized and rescale. But if I train a model and I get like 50%, and I transfer it, it gets 40%. That's like a 10% drop.
Okay.
Right? And then kind of renormalize it so that you can actually get an idea of whether it was like perfect transfer or like terrible transfer. Right? So smaller are like smaller distance, so better transfer. Larger is like larger distance, worse transfer. It's empirical. I mean, theoretically, to study, I mean, essentially here we're trying to answer, we're trying to quantify how heterogeneous modalities are, right? This is one empirical approach and only one approach for all the dimensions of heterogeneity. We call this many dimensions. But it'd be worth investigating like more theoretical approaches or other. When you transfer a model to another, there's going to be some discrepancy in accuracy, right? There's going to be some drop in accuracy. Essentially, we took all of them and then these were kind of just renormalized, right? Like zero means the bucket that there was like no loss in transfer. 1 is like a little bit loss. 5 or 6 means like a huge loss when you transfer. So renormalize to give a intuition on how similar or how different the modalities are. Yeah, we're attacking different things. Right, low rank fusion is more like you have two modalities, like that's kind of fixed, and you already have like homogeneous features, and you're only caring about a fusion. This is really dealing with like in some sense bring heterogeneity to the extreme, where you have like really a huge number of modalities, and these can be robotics, these can be healthcare, that can be like multimedia and so on. So you're really trying to tackle that problem. In fact, if you look at like unimodal models, the C are like interaction models, so you can do like low rank fusion or transformer, right? That's kind of a component. So yeah, other ways of dealing with heterogeneity involve improving optimization. Some folks have found that if you're really starting with very heterogeneous modalities, in this case, RGB from video clips, audio, optical flow. Optical flow basically tracks the motion of things in video. You can try to fuse them, but sometimes fusion is not as good as using each modality alone. Right? So sometimes multimodal doesn't help. And people don't have an exact answer why, but one of the hypotheses was that when you have many different modalities that are very heterogeneous in nature, it can be very difficult to optimize. Right? So sometimes one modality might learn and generalize and kind of learn very well, but the other modalities start overfitting. Right? So they essentially learn at different rates. And that's because different modalities have different complexities, different contribution to the label. It's natural that they will learn at different rates, right? By the time one learns well, the other might have overfitted. So their idea was to compute this overfitting to generalization ratio, essentially tracking across your epochs of training, whether a model is still learning or is already overfit. And that gives you a weight, essentially, to train, to better balance the learning from each modality. One shortcoming there is that in order to compute this like overfitting to generalization ratio, you need unimodal models. You need to know if I just use that modality alone, what is the speed at which it overfits? So I need these unimodal models from each modality, and then compare it to if I have a multimodal model, how much does that modality learn, the speed of learning? And so it's a little bit more expensive. You need to train unimodal models to estimate that weight of how fast the modality is learning and whether it has overfitted, and you can reweight your loss based on that factor. Last method of dealing with heterogeneity, we've talked about many dimensions, one of which is noise, right? Different modalities, if you're trying to learn from the raw data, if you're not starting to process features, the raw data is much more susceptible to different noises. So these folks essentially study the different ways that different modalities can exhibit noise. There's certain noise within modalities, for example, noise specific to your cameras, specific to your time series, and also missing modalities, right? Noise where it's correlated across modalities. For example, if I have a video and there's a blackout, my visual information is gone, my audio information is gone. They're all correlated across time. And essentially, there's still big trade-offs, right? There isn't a clear trend where better performing models are necessarily more robust. And there's several ways of dealing with these. If you want to do fusion in the presence of raw data, you might have to deal with noise. Some ways are, for example, introducing noise during training. If I know that my modalities are going to be missing during test time, in order to mitigate that distribution shift, can I also introduce missingness during training? If I know that different modalities have different types of noise that I might be at risk of during testing, I can introduce these types of noise. I can introduce typos to training. I can introduce random drops in videos during training. I can introduce camera blurs and stuff during training. Another general paradigm of doing fusion is that you can infer missing modalities. Right? I can try to use modality A to predict modality B if I know that modality B is going to be noisy or missing or not going to have perfect raw data. We're going to talk about this more in generation and transfer. So yeah, just to wrap up, we've looked at lots of different methods for representation of fusion. The key idea is still, I have two elements from two modalities. I want to combine them to learn some feature that really takes into account what cross-modal interactions might exist in my data. Is it just redundancy? Is it more uniqueness, more emergence, and emergence at what level? What degree of interaction? So we looked at a spectrum of methods. For more homogeneous modalities, we call this basic fusion. To more heterogeneous modalities, we call it raw modality fusion. And we saw a spectrum of methods. Some of these methods are very simple, more suitable for homogeneous modalities. They are very similar in nature. For example, late fusion or additive, where you're assuming that the features are so similar that you can just add them up and they semantically represent something that is sufficient for fusion. Multiplicative, we want to learn more higher order interactions, going even to tensors and polynomials of higher orders. All these, the weights were still static, right? The W1, W2 for each modality was fixed for all data points. We then looked at cases where the weights may be dynamically changing. For example, gated fusion, or modality shift fusion, or in the extreme case, nonlinear fusion. I concatenate my data and use a big neural network to let the model decide what to learn. But then we kind of revisited and saw you have these big neural networks, you might expect them to learn very complex fusion methods, but sometimes for reasons of the data or for reasons of training, it might only end up learning something similar to additive functions. And then we go more to the more heterogeneous side. If I don't want to assume features, I'm going to start with more raw data. Can I do very early fusion of raw data using more standardized models like transformers? We saw examples of dynamically learning when to fuse, right? Do I do unimodal processing or do I fuse? And you can learn that at every time step using something like architecture search. We saw examples of heterogeneity aware, for example, determining how similar or how different modalities are and using that to decide what fusion strategy. And finally, some tricks